In this section, we'll look at some matrix operations, so how to multiply. I know we looked already at how to multiply a matrix and a vector, but here's going to be a matrix and a matrix. Some more terminology, how to add matrices and a scalar multiplication. So this is a generic matrix. This A11 is the first entry. It's 1, 1 because it's row 1, column 1. So every entry is in some row and some column. So if you're writing it out generically, like A, I, J, it's row I, column J. So that's a generic way to write a matrix. We always talk about an M by N matrix, where M is your rows and N is your columns. And you can also write A in terms of its columns. So notice that the entry has 2 subscripts, but a column has just 1 subscript. So it can be written in terms of A1, A2, and these are vectors. You have the arrows over top. So these are columns. So this would be the vector A1. A diagonal matrix is a square n by n matrix whose non-diagonals are all 0. So you might have like 1, 2, 3, 4, and then you have zeros everywhere else. So this diagonal is the only non-zero entries. Now one of the diagonals could be a 0, but all the ones that are off the diagonal have to be 0. In terms of, I use MATLAB notation. Oftentimes I use diag of 1, 2, 3, 4. So that tells you it's a diagonal matrix where the diagonal entries are 1, 2, 3, 4, and so you just know that all the rest are zeros. The identity matrix is a diagonal matrix where all the diagonal entries are 1. So it's 1, 0, 0, 1 would be I sub 2. So this sub 2 tells you the size, that it's a 2 by 2. So the 3 by 3 would be 1, 0, 0, 0, 1, 0, 0, 0, 1. And then I4 is a 4 by 4 identity matrix. So 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1. So you'll understand later why we call it the identity matrix. But again, the identity is a diagonal matrix whose entries are all 1. When we use E, that's referring to a unit vector. So E sub 2 would be the second column. And if we do E sub 2 on this one, it would be 0, 1. The second column for I3 would be 0, 1, 0. And the second column for this one is 0, 1, 0, 0. Notice that E2 by itself doesn't tell you the size of the vector. We say 2 matrices are equal if they have the same size and all their corresponding entries are equal. So if I had 1, 2, 3, 4 equals A, B, C, D, you know that A is 1, B is 2, C is 3, and D is 4. Otherwise, they wouldn't be equal. In this first exercise, we're going to do some computations. Again, these work the way we expect them to. If you multiply a matrix by -3, that's going to multiply every entry in your matrix by -3. So that's going to be -3, knowing that this is A, -3, -6, +6, -3. This second question says 2 times the identity matrix, and this sub 2 tells me it's a 2 by 2. So it's 2, 0, 0, 2. Multiply to every element in the identity matrix by 2. So I'm going to add B and C. So I have 3, 5, -1, 4, plus -5, 3. They are not the same size, so this is not possible. So 2i plus a, I'm going to write 2i, so that's a 2 by 2 with 2 on the diagonal, plus A, so 1, 2, negative 2, 1. And to add, we're adding the corresponding pieces. So 2 and 1 gives me 3. 0 and 2 gives me 2. And I have negative 2 and 3. This theorem 1 tells you like how to behave. This theorem 1 gives you some properties. This first property tells you that you can commute when you add matrices. This second property is the associative property for addition. This third one is that 0 is the identity, the additive identity matrix. So keep in mind when we write 0 here, that really is the 0 matrix, and it's whatever size A is. So it's not just the number 0, it's a matrix with zeros in it. This property tells you can distribute a scalar over addition. And this property says you can distribute a matrix through the scalars. And this property tells you the associative property with the scalars. We've touched on matrix vector multiplication, and we looked at writing it as a linear combination, and we've also looked at what I call the dot product method. Both those methods will work for matrices, but the writing it as a linear combination is a really long way to do it. We are going to look at more the dot product method. And first, is this defined? So if A is a 3 by 2 and B is a 2 by 2, so I'm going to do 3 by 2 times a 2 by 2. These match, so we're good. So that tells me that the outcome is a 3 by 2 matrix. Is BA defined? So I have 2 by 2 and then a 3 by 2. These inner dimensions do not match, so not defined. So notice right away that AB does not necessarily equal BA. Like one could be defined and one isn't defined. This may be the first object, mathematical object, that you've seen that is not commutative over multiplication. All right, they're calling this the row column rule. I call it the dot product rule. Here's the formal rule. I like to look at it visually. I take the first row and do the dot product with the first column. So dot product means you multiply your first components and add it to the multiplication of your second. So A times G plus B times K, and that's where this comes from. So for any entry, so let's look at this one. It is in row 2, column 3. So I'm going to take row 2 of my first one and column 3 of my second one. And I'm going to do the dot product. So that tells me C times I plus D times M. And that's where that entry comes from. Let's compute AB. So I'm going to take my first row and my first column. So that's going to be my 1, 1 entry is going to be 4 times 1 plus negative 2 times 2. And I'm going to take my first row times my second column and do the dot product. So 4 times 3 plus negative 2 times negative 1. Row 2, column 1, dot product would be negative 3 times 1 plus 0 times 2. Row 2, column 2, I'd have negative 3 times 3 plus 0 times negative 1. Then row 3, column 1, 3 times 1 plus 5 times 2. Row 3, column 2, I have 3 times 3 plus 5 times negative 1. So you can kind of see a pattern if you do it the same every time. So 1, 2, 1, 2, 1, 2, 3, 1, so you can kind of see those patterns. So in this case, I have A is a 2 by 2 and B is a 2 by 2. So I can multiply both AB and BA. So if I were you, I'd stop now and try to compute these yourself, and then check your answers with mine. Again, notice that these two are not equal. I'm going to say notice, not equal. So AB is not equal to BA. So again, just writing out that that is not true. Another kind of weird or interesting thing is that the zero property of multiplication does not hold. Maybe I should review that a little bit. So the zero property basically says that if you have two numbers, A, B equal to 0, so A and B being real numbers, not matrices, just numbers, that tells you that either A is 0 or B is 0. And when you're solving quadratics, you use this a lot. In matrix world, that is not true. You can have two non-zero matrices that multiply to be equal 0. So again, if you have A times B where A and B are matrices equaling to 0 does not mean that one of them is 0. And so that also means that cancellation law does not hold. So if you have A B equals AC, it is not true that B equals C in general. It could be, but it's not guaranteed. Another way to do multiplication would be to think about this second matrix as a list of columns. So instead of writing B as a matrix, you have B1 as the first column, B2, all the way to the end, how many columns B has. And then you can kind of distribute the A to each of those vectors. Okay, so A is a 2 by 2 and B is a 2 by 3. So I can multiply them. I can multiply A and B. And BA, notice, is not defined. I'm going to say no. But AB we can compute. And just to show you how this definition works, if I multiply A times B1, B2, B3, that would be the matrix 1, 2, 3, 4 times the vector 1, negative 3. That would be your first column. The second column would be 1, 2, 3, 4 times your second column. And then you have 1, 2, 3, 4 times your last column. And then you can use matrix vector multiplication, whichever you prefer. Theorem 2 gives you some properties for multiplication. So this first one tells us that the associative property still holds, so you're not changing the order. The distributive property over matrices works, but they call it the left distributive law because you got to keep the matrix that you're distributing on the left side. And it also works if you keep it on the right side, but you can't swap that order. You can move the scalar around. And then the identity times any matrix is itself. So that's why it's called the identity matrix, because if you multiply any matrix by the identity matrix of that right size, you'll get that matrix back. Another operation of a matrix is the transpose, and it's denoted with the exponent of a t. So you would say this would be called A transpose. And you swap the rows and columns. So if I'm going to compute the transpose of A, my first row is 3, negative 6, 4. Well, that's going to become my first column, 3, negative 6, 4. Row 2 will be my second column. And then the third one. So that is A transpose. So B transpose, the first row would become my first column. Second row, second column. Here, notice that the size changes. B originally was a 2 by 3, and B transpose is a 3 by 2, which should make sense because you're swapping the rows and the columns. And there's lots of properties we have associated with transpose. So if you take the transpose and then transpose it again, you'll get back to A. The transpose is distributed over an addition, and you can bring a scalar in or out, it doesn't affect it. But when you take the transpose of the product, notice that it swaps the order of the transpose. So If you multiply first, then take the transpose, that's the same as taking the transpose of each individually, but swapping the order. So lastly, I want to find the transpose of AB in two ways. So our goal is to find AB transpose. So one way would be to multiply the two matrices first. So go ahead and multiply those two. And then we can take the transpose. The second way is to use B transpose times A transpose. So I'm going to write down B transpose first. So 3, negative 2, and then negative 2, 1. Notice that B is equal to its transpose. So that happens if your off diagonals are the same. A transpose would be negative 1, 2, 5, 4, 2, negative 3. And now go ahead and multiply those. And notice that they are the same. So we just really verified that last rule that we had, that AB transpose is equal to B transpose A transpose.